everybody. Welcome to the inside of the Planetary Society. We're doing a Facebook Live today in honor of the 40th anniversary of the Voyager missions on this, the 40th anniversary of the launch of Voyager 1. I am Danielle Gunn, Communications Manager here at the Planetary Society, and while we're waiting for people to join us, we would love if you could share or like this video so that more people can see it and learn about space, and especially Voyager, because we have two very special guests with us today. To my far left is our planetary evangelist and senior editor, Emily Lakdawalla. Hello. And this very special person here is Dr. Louis Friedman, who in 1980 co-founded the Planetary Society with his colleagues Carl Sagan and Bruce Murray. So we're very excited to have you here. He's also the author of many books and articles, including his most recent Human Spaceflight from Mars to the Stars, and he also serves as our Executive Director Emeritus at the Planetary Society. And I'm sure you have lots of awesome Voyager stories to share with us today.
I remember it.
You remember it, so that's why we brought you in. And so this is your opportunity to ask us questions, and you can comment, make questions here in the screen, and we would love to answer those for you today. First, I'll start off by asking Emily, what is so remarkable about this mission? Why do we want to keep celebrating it?
Well, I think Voyager, for a lot of people who are into planetary science, was the thing that just energized us about the exploration of our solar system. I mean, just consider a single mission opened up half of the solar system to us. Mm-hmm. We had the flybys of Jupiter and Saturn, which the pioneers had visited, but not with cameras like the Voyagers had. And then we visited Uranus and Neptune for the first time. A lot of the people who are currently working on outer planets missions were students at the time of the Voyager missions. I was a kid at the time of the Voyager missions, and for me, exploring these strange new worlds, seeking out new landscapes, discovering new moons, finding every single moon being a different and exciting place, for me, that was why Voyager is so exciting. But I think for Lou, and for the Planetary Society, Voyager is even more than that, because Voyager and the Planetary Society really kind of grew up together. So I'm wondering if you can talk a little bit about that.
Well, very much. Voyager is intertwined with our history and my personal history, as well as the history of the society. We were formed in 1980 when the Voyager mission had just coming up to Jupiter in 1979, and the whole reaction to this great voyage was the government isn't going to do planetary exploration anymore. And that's when Carl Sagan and Bruce Murray got together and said, we have to do something about this. The interest in the exploration of the outer solar system, the interest in Venus and Mars is enormous, and the public wants more missions, and that's why we formed the Planetary Society. So practically on our first month of formation, we were given an enormously important function: celebrate the encounter with Jupiter with a big dinner, gala dinner, and invite people into that. And that's actually the first function we ever held, was celebrating the Jupiter encounter. And then a year later, we celebrated the Saturn encounter, or I guess it was more than a year later, 2 years later, with a Planet Fest, and that helped the Planetary Society get known in a big way. And we celebrated all the encounters the Voyagers had, at least so far, and Jupiter and Saturn. The Uranus encounter, we did an event at Caltech, and the Neptune encounter, we did a grand party at JPL that really invited a lot of people to, and had a great deal of attention. So we not just celebrated the encounter, but brought home these wonderful pictures. And before the internet, you handed out pictures on paper to people who came, and the public didn't have access to those pictures in those days. So it was an important role for the Planetary Society to essentially bring the results of solar system exploration to the public.
And we, through a member magazine, the Planetary Report, we often delivered people their very first views of all of these different worlds. And I went back and read through a whole bunch of back issues of the Planetary Report to read what Bruce and Carl Sagan were writing about the various encounters. And it's kind of interesting how each time the Voyagers passed by a planet, it had been a few years since the last one, different things were happening here on Earth, and you found that you and the other founders kind of in a reflective mode about how the Voyager encounters at the different planets were kind of a touchstone for events also happening on Earth.
Well, that's very much true, and I should mention that Bruce and Carl were very much involved. In fact, one of the strong founding principles of the Planetary Society was to bring the participants in the space program, the scientists and people who were working on the missions, together with the public, so that there could be a feeling that everybody could participate in some way or another, and that Bruce was director of JPL at the time. JPL was carrying out the missions. Carl was on the Voyager team, was one of the major scientists involved in seeing these first pictures from these outer planets and the moons of the outer planets, and was very involved in both the science of the mission and in the public explanation of the mission. So it was an extremely important time, but as I say, it was intermixed with this strange position of the U.S. government, which was, well, let's cut out planetary exploration. Well, as if been to Jupiter, and no, we don't have to go any further. And of course, the public reaction was just the opposite. And so we were dealing constantly with these political issue. We want more exploration. We want a mission that would orbit Jupiter, which became Galileo. We wanted a mission that would orbit Venus, which became Magellan. We wanted future exploration of Saturn, which became Cassini in later years. These things were all in doubt at the time that the spacecraft were making the encounters.
That's interesting that you mentioned Cassini, because of course the Cassini mission is going to be ending in less than 2 weeks after this hugely long and successful mission, all these amazing images it's returned from Saturn. You know, when the Pioneers passed by Jupiter and Saturn, we had the Voyagers on the way. When the Voyagers completed their exploration, we had Galileo on the way. When Galileo was done, we had Cassini on the way. Now there's Juno, but it's a smaller mission, and we don't have another flagship that's currently in space on the way to another planet. For me personally, I want to go to Uranus and Neptune. I want to keep on in the tradition of Galileo and Cassini and get orbiters at Uranus and Neptune and see those next. Why do you think, what failed? You know, why don't we currently have those next orbiters on the way? Is that the wrong goal? Should we be doing something else, or do we need to keep fighting for those kinds of follow-on missions?
Well, one of the chief reasons that the public is so interested in space exploration and the sort of a driving, you know, why is it worth spending billions of dollars on any of these missions? And the whole question is because we want to understand our relationship with the universe. And Carl Sagan said it once, we're looking for ourselves out there. The question of life on other worlds, the question of how life came to this world, and the future of how human life might evolve off of this world, these are the driving questions. And these are what we're answering when we get out there in these missions. Certainly Mars is relevant. What we didn't expect, and the Voyager brought it home so graphically, made it so important, even beyond just the stepping out into the solar system, was that these moons around Jupiter, I mean, I couldn't have imagined it, that the idea that those moons are relevant to astrobiology, that they are relevant to the questions of life. Those moons are supposed to be cold, dark dots in the sky, and instead they're active, exciting worlds. And that's the reason we went out exploring, is that these questions relate to how life might have formed, what are the conditions for life, what is the questions of habitable worlds. These are still unanswered questions. We talk a lot about it, but they're still unanswered questions. And we found that very dynamic worlds, Io with its volcanoes, and Europa with the how do you say that? Under ice ocean. I can't say underground ocean. Under ice ocean. And Ganymede probably has liquid water inside of it as well.
Even Callisto may too.
Yeah. Oh, okay. There's a tremendous amount of relevance out there to these really driving questions that are worth spending billions of dollars on, and that is, what is life, and and how did it get here?
Mm-hmm. Speaking of questions, we have some from our Facebook audience, and if you have questions, please put your question in the comment box next to the video. There are some really great questions here, and one of the basic ones that a lot of people are asking. So Brad Arnold, thank you for your question. If Voyager continues on its current path, what will be the next astral body encounters? Maybe we could talk about where are the Voyager spacecraft now, and where are they going?
Well, I could cop out and just simply say, I don't know, and then be silent, but I'll say a couple of sentences on that. And then Voyager, of course, is headed out on a hyperbolic trajectory, that is, on a straight line away from our solar system, and it will someday encounter other star systems. I believe the estimate is as many tens of thousands of years from now. So I can't tell you the name of the body. I think somebody does know the name of the star that system that it is headed toward. But it's a very interesting question, because on one hand, Voyager is our first interstellar voyage. It's in the interstellar medium. Now, having said that, I must emphasize it's still in the solar system. It is still gravitationally bound to the sun. It would be until it got out the distance of the Oort cloud, 100,000 AU or something like that. So in that sense, it's still in our solar system, but it's in a part of the solar system now which is dominated by interstellar particles that come in from other star systems. And in that sense, it's in the interstellar medium, and it is our first interstellar Voyager. So it's going to be a long, long time before it encounters another celestial body. And maybe you know the answer.
Well, and also encounter is a relative term,
Yeah,
so
right.
we're still talking about passing at a very great distance from any other body. The one thing that I think that does boggle a lot of people's minds is that even though Voyager is on an escape trajectory, it's flying away from our solar system, it's still gravitationally bound to the galaxy. So it's going to orbit the galaxy for as long as there is a galaxy, so until the heat death of the universe, pretty much. So that's kind of cool and interesting.
Isn't Andromeda eventually going to clash with the Milky Way? Maybe?
Actually, I think you're right about that.
Yeah,
So yeah, maybe
you can catch a ride on Andromeda.
Right.
Two other really great basic questions that I'm curious to know too is Lindsay Baker asks, does Voyager still send pictures or any other data? And Mike French, of course it sends data, but photos, I don't think we maybe get anything. And Mike French asks, how many light hours does it take to get a signal back?
Well, it is sending data, and we are in communication with it, and that's how it was discovered that it went into the interstellar medium. They actually saw the shock as it passed through the part of where it's flying through the bow shock of the solar wind as hitting the interstellar medium. So they noticed that in the data. So we do get data from Voyager. I don't have the answer immediately in my head as to the number of hours of the signal. I guess we can sit here and calculate it.
It's roughly 2/3 of a day, because it has to do with, you send a signal from one of the Deep Space Network stations on Earth. It goes all the way to the Voyagers. It takes roughly 2/3 of a day, and the reason that I know that is because you have to you spin past one of the Deep Space Network stations and then another one in order to, that's how much time it takes a signal.
But the important, Voyager's roughly 130 astronomical units from the sun. And it takes like 8 minutes to go 1 astronomical unit, so we leave it as an exercise for everyone to do the math.
We didn't answer the question about the images. So the spacecraft no longer take images. They are powered by these radioisotope thermoelectric generators that are slowly decaying over time. And so their power output is decreasing over time. And so over time, the engineers have been shutting down one instrument after another in order to conserve enough power to keep the most important things, the spacecraft health, the computers, the radio, and then certain instruments are still running. There was a very last image taken by the Voyager spacecraft, and that was the famous pale blue dot photo taken by Voyager 1 on Valentine's Day 1990. And in reading some of the past planetary reports from the Planetary Society, and reading what Carl Sagan had to write about planning that, I realized that he had been planning that image for a really long time. And I'm wondering if you have any memories about that, about his vision for the pale blue dot image, what it would be like and what its significance would be later.
Well, I certainly remember the planning of that and the campaign to make it happen. The fact that the Voyager, first the Voyager team didn't want to do it, and NASA didn't want to do it, and then the case had to be made for it. It was a rather controversial discussion because it entailed some risk. The spacecraft had to be moved to take the picture. It had to turn around and take a picture in another direction, and at that kind of distance there was some concern that maybe they would lose it, something would go wrong. So that's my major memory of it, and major memory, of course, of the impact. We did a whole feature on it. Carl very much explained it, and we made a great poster of it as well. I remember.
Do you remember where you were when you first saw that image?
Oh boy, I'm sure I was. Well, I was going to say here, but we weren't here. No, I'm sure I was in the office when we saw that image, the Planetary Society office, because it was something we were anxious to await. And the pale blue dot, it's enormously significant because, like I was saying earlier about the satellites of the outer planets, all these astronomical objects, at one point, are just dots in the sky, and they almost seem insignificant. And then you realize the significance when you look at Earth and everything that's happened on Earth, and all of all that we know of is here on that pale blue dot. So no, it was a powerful image.
Yeah. People are commenting on our model here. What's the story with this guy? It's such a cool model. And this is a Voyager. Is it represent 1 and 2?
It's the same spacecraft. It's a prop. It's a beautiful prop. It's a really high fidelity model of the spacecraft, and you can see many of its instruments. A couple of interesting things to point out about it. One is that all of the cameras are on this scan platform thing here down at one end, and that scan platform could be rotated in order to take pictures as the spacecraft kept its orientation in space, so that they could point the radio antenna in one direction, other antennas in different directions, and then they could spin the scan platform to take photos. That didn't always work perfectly. In fact, there was I believe it was the Uranus flyby when the scan platform stuck. I may be remembering the wrong flyby, but at one point the scan platform stuck, and they actually lost the opportunity to take a lot of really close-up pictures of some of the moons because of that. And so other spacecraft have made different choices. Like Cassini, for instance, does not have a scan platform. All of its cameras are bolted firmly to the side of the spacecraft, and so they have to rotate the entire spacecraft in order to take a picture with Cassini. So that's just one little. Another thing is that if you see these teeny little antennae right here.
Before you start with the teeny things, say what the big things
are.
Oh,
the big thing. Well,
because you got to get oriented with the big things.
Well, that's true. So this is the very most important radio dish. This is what we get all of our transmissions to Earth through. This guy, the transmitter behind it, has a power of 20 watts. That is a very dim source for all of the data that's being sent back to Earth.
Think of a 20-watt light bulb.
It's a light bulb, less than a light bulb.
Yeah, it's less than a light bulb. And that's how we get all of our signals. And so in order to get all of the data back from Uranus and Neptune on these missions, they had to build the dishes on Earth bigger in order to receive them. Originally, there were only, I believe, 30 or 35-meter dishes. They built originally the biggest dishes at the Deep Space Network were, I think, 64 meters?
64 meters.
And then they had to actually expand the dishes to make them 70 meters. So there's at least one of them that they can't actually rotate the dish all the way as down to the horizon, because otherwise the edge of the dish would whack into the ground.
But so the antenna, this is why the spacecraft has a large antenna. Even with those large dishes, it's 20 watts to get the signal back. And then these are the radioisotope thermoelectric generators that provide the nuclear power that powers the spacecraft. Solar power couldn't be used because the spacecraft goes way beyond the solar distances where the sun would be an effective power source. But then the largest device is all the way out there on that long boom. And I'd like to explain it, but it's a scientific instrument, so I'm going to let you explain it.
You're putting me on the spot.
No, that's the magnetometer, and the magnetometer out there. And you put the magnetometer way far away because you don't want it to get messed up with the readings of all the metal and other element and the other devices that are the electric and the magnetic fields that are around the spacecraft. So you get that far away from the spacecraft, and so that was a huge job. And of course, when the thing was launched, this was all packed up into a shroud on the rocket, and then everything had to be deployed: the antenna, the long boom, the booms that the RTGs are on, and the scan platform.
The reason that I was pointing out these dinky little antennae is because I make models of spacecraft just for fun in my spare time, and these are little, there's two little radio and plasma wave antennae that are at 90 degrees to each other, and you can look and find the exact same antennae on both Cassini and Juno. They're the same instrument. The legacy they're essentially the same instrument run by pretty much the same group of researchers at the University of Iowa, and it's been you know, if it ain't broke, don't fix it. You put the same instrument on multiple spacecraft, and you get to have the same kind of data set from many different places, from many different missions.
If you're just joining us here at our Facebook Live, we are celebrating the 40th anniversary of the Voyager missions. I'm Danielle Gunn. We're with Emily Lakdawalla, our senior editor and planetary evangelist, and Lou Friedman, co-founder of the Planetary Society, and we're taking your questions about the Voyager missions. And one of those questions, as we talk about the model, is how does it avoid, this is Hazel Mitchell, thank you for your question, do the Voyager probes actively avoid space debris? How would that work?
They don't avoid space debris, but they are hit by space debris as they go along. So far, as far as I know, there's been no major effects from space debris. There's very little. Space is a vacuum, and there's very little micrometeoroids that will hit the spacecraft. It does have protection against that, and in principle, there could be damage from it, but I don't know of any damage that's ever occurred from that. But space is pretty empty, and these spacecraft, as they've flown out to the solar system, have managed to avoid getting hit by any damage. I need to also say something about the 40th anniversary. Today is the 40th anniversary of the launch of Voyager 1, but it's actually was a couple of weeks back, maybe a month ago, that the Voyager mission began with Voyager 2. Everybody always wonders, why did Voyager mission begin with Voyager 2 and not with Voyager 1? Voyager 1 is the spacecraft that arrived at Jupiter first, but was the second one to be launched because it went on a slower trajectory. And so, yes, today is the 40th anniversary of Voyager, but we're late on getting the announcement out about the Voyager 2 anniversary.
And we've been celebrating with lots of content that Emily has been curating, and some people are asking about better, slower explanations of all the pieces of this, and I am sure in our blogs, planetary.org, we can find all of this information in there. In
fact, I've posted, one of the first blog entries that I posted in the Voyager 40th anniversary included a really long list of wonderful archival material. So it includes press kits made by NASA and JPL for the launch and every single planetary encounter, press releases, fact sheets, every question that you have about what all of these machines are and how all of their parts work is answered for you in language that was written for the media. So it was written to a general audience level. This is not just for engineers, so do go check all that out.
A really fun question came up by Jason Campbell Cook. If there was a chance to do the Voyager mission all over again, but with today's technology, what would you change or add to the spacecraft or mission?
Nothing.
No, I have answers to that. So one of the interesting problems with the images that we have from the Voyager missions is that the camera technology that they carried and the optics in their instruments were not capable of detecting long wavelength light. So, light is on a spectrum. It goes from redder is longer wavelengths, bluer is shorter wavelengths, and beyond red it goes into infrared, very long wavelength, and beyond blue it goes into very short wavelengths, ultraviolet. The Voyagers could see in ultraviolet, but they couldn't see in infrared. They couldn't even see red. So the images that we have of Jupiter and all of its moons from the Voyagers aren't quite natural color. They're not quite the colors that the human eyes see because they're not sensitive to red light. The other reason this is important is because infrared light is really useful for penetrating hazy atmospheres. So without the ability to see in the infrared, we couldn't see through Titan's atmosphere. And we also couldn't see through the high hazes of Uranus's atmosphere. So Uranus famously looked really boring to Voyager 2. But there's actually a lot happening underneath the very top layer of the atmosphere. And if it had been able to see just a little bit longer wavelength, Uranus would have looked much more exciting. And we would have been able to see much more deeply into Neptune's atmosphere. And we might have discovered some of those lakes on Titan way back with the Voyagers if they'd carried camera detectors and instruments that were able to see longer into the infrared.
The other thing that's changed, of course, is the communications rate has gone way up in more recent years with higher frequency communications than was employed in Voyager. And so I suppose we would be employing the higher frequency communications devices as well. On the other hand, the RTG power sources are roughly the same now as a little bit more efficiency. Still a difficulty in getting the fuel to keep the production of RTGs available. But the question I would have is the size of Voyager. Is the scale here on this?
It is.
It's 1/2 inches 1 foot. So
Yeah, so it's a factor of 25
Yeah.
or so in the scale. And in Voyager, when you see the full-size spacecraft, would occupy much more than this room. And the question I would have is if you had to make it all over again, could you make it smaller? And I don't actually know the answer to that. It's a question that I've been poking at a lot of people, which is how small can we make interplanetary spacecraft and still keep them reliable? Because Voyager has a very reliable, robust system that can take glitches in the computer and glitches that happen along the way and recover from them and be reset.
Here's a question from Mark McLean. Who manages the data coming back from Voyagers Today and on into the future?
I can take that. So the data from Voyager and all planetary missions, and all actually NASA missions, is managed by NASA initially and managed by the mission. They receive the data, they verify it, make sure that they got every bit from the spacecraft that they wanted to get. They'll ask the spacecraft to retransmit if they need to. And then once they verified the data and made sure that it meets all of their standards, they put it into something called the Planetary Data System, which is a public repository of all of the data. So one of the most wonderful things about NASA missions, and this is also true of ESA missions as well, is that the data are public. Anybody can go into these archives, pull out the data, and see images that actually not a lot of people may have seen, because the more modern spacecraft are sending back so many data bits that very few people actually have a chance to see it all. But even Voyager, which returned not that many images from, say, Uranus and Neptune, you can still find surprises. You can still find images that you're not familiar with if you dig into the archives. And of course, that's one of my main things that I'm super excited about. And also, with modern image processing technology, discoveries can be made in Voyager images even today. So one of the cool, most recent discoveries has been new regular moons at Uranus. And there's a scientist who has done this work, Mark Showalter, where he has basically unwrapped the rotation of all of the bodies in the rings of Uranus. And this isn't easy to do. It's not just a matter of rotating it, because everything moves at different speeds depending on how far away it is from Uranus. So you have to sort of despiralize all of the images, make them all line up, stack them, and then you can discover new moons, and that's what he did, which is pretty cool.
As the WHO manages it, the whole project is still managed at JPL.
Mm-hmm.
They still have a project manager after all these years, and they still get responsible for monitoring the health of the spacecraft every day. And so it's a small activity, because right now you don't get a lot of data, but on the other hand, you do have to monitor it. So the project is managed for NASA at JPL and continues to be an active project, and will be at least for another 5 or 10 years.
At least 5, I think now it's at least 10 years.
Okay.
Mm-hmm.
We're getting a lot of questions, of course, about one of the things everybody knows Voyager missions for so well, the Golden Record. And as you were friends and colleagues with Carl Sagan, who helped lead that project, do you remember what was the first time that you heard about the Golden Record concept? Do you remember it?
Well, the Golden Record, of course, precedes the Planetary Society,
Mm-hmm.
because Voyager, actually, the launch precedes the Planetary Society. So I was not part of the team that initiated the Golden Record. On the other hand, it had an enormous influence on us. The whole idea of sending a message on a spacecraft and of selecting what you send is something that the Society has done many times over the years. The creative director of the record was John Lomberg, who was an advisor to the Planetary Society, and then of course Carl was the leader of the project. Andrean was involved. Barney Oliver and Frank Drake were involved. They were also advisors to the Planetary Society, and so it had an enormous effect. In fact, those people who I just mentioned actually came to us when we were starting the Society and said, we published a book about the Voyager record, and it's making a little bit of money, and we can't keep the money because it's really a NASA project, so it doesn't belong to us. How about we give it to the Planetary Society and help them get started? So we have a little bit of roots in this as well. John Lomberg went on to create the Visions of Mars. That was a Planetary Society message, or not a message, but a library that we put on Mars as part of the Phoenix mission. And so there's another, it led to a number of projects where we send out some representation of the planet, some representation of our thinking as it goes out to other worlds, maybe to be discovered by some extraterrestrial life in the future, maybe to be discovered by ourselves in the future as we explore the solar system. John is involved now with another Outer Planets project, sending something called the One Earth message as part of the New Horizons mission, and trying to, again, take the ideas in the record and elaborate upon them, which is so much more possible now through all the modern internet communications we have.
Excellent. We're going to take one last question before we sign off. I just want to thank you guys so much for joining us today. We are trying to do these Facebook Lives more regularly because it's an amazing opportunity to get to talk to the experts and the people who were really there. And we know all of you that follow us are just as passionate about space as we are. I also want to encourage you to consider joining the Planetary Society as a member. You can visit us at planetary.org/join. And we have a lot of Voyager material collected and up on our website, planetary.org, where you can hear many personal stories of what it was like to be behind that mission when it happened. Lots of new images and videos, fascinating videos and images that have been processed by the space image enthusiast community. And so, again, we really, really thank you for joining us, and also would love to hear other ideas you have for things that we can do here on this wonderful new platform with Facebook Live. So leave those comments below, share the video, like the video, help us get the word out so that we can bring more space to you and all your friends. So rock on. Thank you, Dylan. Thank you. Cheers from Alan. Hazel Mitchell, thank you. All right. Let's see, I'm trying to dig around for, oh, here's a great little last question. Who came up with the name Voyager? David Hamilton. Do we know?
That's a good question. I'm not prepared to answer that. I will say that when I started at JPL working on this mission, it was actually not called Voyager, it was called Grand Tour. Voyager was a previous name of a previous project which also didn't get to fly. It was the previous name of the Viking Mars mission, and it was a mission that was going to go to Mars. So that name had been tested and then not used. And then the Grand Tour that we were working on was a mission that was at the time designed to go to Jupiter, Saturn, Uranus, and Neptune. What a crazy idea to have suggested in the late 1960s and early 1970s. And to do it with a spacecraft that was autonomous. It was called a thermoelectric outer planet spacecraft. And because thermoelectric, because it was using the power of the RTGs. Well, that mission got canceled. It was too expensive. And all of us at JPL were kind of, it was a blow. I remember I was working on the navigation system, and I was presenting a paper on the navigation system the very day the project was canceled. But over the next weekend, some really bright people got together and designed a scaled-down version, a mission that would only go to Jupiter and Saturn, and it was going to be called the Mariner Jupiter-Saturn, and it was going to be very limited in its capabilities. It wouldn't be fully autonomous, but JPL pulled the wool over the eyes of everybody by designing a very capable spacecraft. It went beyond Jupiter and Saturn. It became Voyager, and the rest is what it's doing today. It went to all of the planets that we intended to on the Grand Tour.
Excellent. Any final comments before we sign off?
I'll just say that it's just such a pleasure seeing the international community of amateur space imaging enthusiasts that you mentioned continuously diving into the data, finding new ways to make it beautiful, and inspire us maybe to think about how we can follow on Voyager with future exciting missions of discovery.
Mm-hmm. Yeah, and I emphasize a point I think I made earlier, which is the real change that happened with Voyager is it brought little dots in the sky to become whole worlds with interesting dynamics, interesting stories, processes that are going on that we didn't even know existed. There was an enormous change, not just in understanding science, but understanding our universe from a much broader perspective.
Excellent. Thanks again, everyone, for joining us. We're really thrilled to have you here, and all your questions and comments. Please share this video with your friends so you can help them learn more about the amazing things that we've discovered out in the cosmos. I want to say thank you to Andrew Polly and Chelsea Bell and Brandon Schultz and Matt Kaplan for technical support. And we will be back on Thursday with Dr. Bruce Betts and Bill Nye, our CEO, to talk about light sail. So please join us. We'll be sharing info about that Thursday afternoon. And so for now, we're signing off. Bye.